We're only seeing your beautiful face.
Thanks. Let me try. I guess now you see it, right?
Right now I'm seeing blank. There we go. Yep. Okay, you're good to go.
Oh, thank you. So, okay, first of all, thank you for the invitation. It would have been very nice to be in Vienna in this time of the year. I know it's a perfect time for visiting. So I hope there will be soon an opportunity to visit physically the institute and the town. So I'm going to talk about thermodynamics of a quantum annealer. This is work that I have done at the University of Florence. And here I'm also adding my new affiliation as I just moved to Pisa in the Institute for Nanoscience of CNR, so still in Tuscany. So the main idea here was to try and understand something about the thermodynamics that is involved in quantum computation. And in particular, we carried some experiments, so to speak. In fact, they are experiments on a quantum annealer. And the guy who actually ran the experiments is Lorenzo Buffoni, who is a PhD student at the University of Florence. And he has spent some time at D-Wave company in Canada and learned how to program this quantum annealer. So here you see the archive reference, and there is also QR code. If you want to scan it with your smartphone, you can get the paper right away. The paper has been accepted today in Quantum Science and Technology, so it will be published there soon. So just briefly, let me tell you a few words about the processor. It's here in my selection. You see a picture of the chip. Of course, the technology here is not semiconducting technology, but it's a superconducting technology. So there are superconducting circuits patterned on the chip, and you have to keep it at a very low temperature by putting it into this cryostat, which then goes into a bigger box, black box here. But the interesting thing is that through a cloud service, you can access the chip, meaning you can initialize the chip, you can run some driving on it, and you can read out. So that's what Lorenzo did. And as I said, the purpose was to study the energetics of the typical operation of such processors. So let me just tell you a few words, because maybe not all of the people in the audience are familiar with such quantum computers or quantum annealers. The basic logical brick here is the qubit, and in particular in this device, it's the flux qubit. It's a superconducting ring, basically, interrupted by Josephson junction. And it has two low-lying energy eigenstates, one where the current circulates counterclockwise and the other is circulating clockwise. And the next, so the higher energy levels are a little far apart. So in first approximation, you can really treat this as a two-level system. It's like a spin, a one-half spin. So there are two relevant quantum states, and then by manipulation of those states, superposition, entanglement, and all that, one can perform quantum logical operations. Just to give you an idea, the chip is organized in plaquettes, which are this guy here, composed of a certain number of flux qubits, and then the plaquettes are linked one to another forming a graph, which is called chimera graph in this specific implementation, and that's what is patterned in the chip. And here you see all the wirings that allow you to manipulate the qubits and to read them out. So it's a platform for quantum many-body system which can be manipulated remotely. So that's a nice thing. We can now, as theorists, we can do experiments by these cloud services. So a few more words. What people do with these devices, they do a thing called quantum annealing. Namely, the idea is the following. You see here in yellow and green, there are two Hamiltonians, one along sigma x and the other one here along sigma z. And you have this weighting parameter 1 minus s and s. So you change this s in time and you switch from hx here, you switch from hx to hz by manipulating this s in time. In other words, if you start, for example, from the ground state of the x Hamiltonian and you change this parameter s slowly in time, you will find yourself in the ground state of this other one. So, and that's could be, for example, a state in which you encode a problem that you want to solve. So this is basically what people do with it. And our idea was to study, as I said, the energetics of such annealing protocols. So what is the energy that you spend to run such annealing process? What is the energy that you exchange with the environment, and so on and so forth. So let me show you this slide here where I basically list what kind of the interactions that your system has with the outside world. So your chip interacts with basically your driving. Yeah, here this green thing is a work source, which is responsible for this time dependence in the Hamiltonian of the chip. So you change this s in time, and accordingly you are doing work on your system. You're exchanging energy with it in the form of work. At the same time, your chip is not exactly isolated, and our experiments, in fact, show this very clearly. In other words, the dynamics is the dynamics of an open quantum system. So the chip is in contact with the thermal bath, bath at some temperature, which we call T2. It interacts also, you can interact with it by preparing the state of your system. So this is preparation here. You can prepare your initial state, for example, this one, or any other eigenstate of the sigma z operators here. And then you also have the possibility to read the sigma z Pauli expectation of the Pauli matrices, the Pauli operators at final time. So after you have run the time-dependent driving here, sorry, I cannot. Yeah, there it is. After you do the time-dependent driving, so you have exchanged some energy with your chip, and your chip also has exchanged energy possibly with the reservoir. You can read out a final state, for example, this one. Now, we have full freedom in the preparation. So we decided to prepare the initial state according to a certain Gibbs distribution. Namely, we pick up a certain state with certain probability given by the Gibbs factor associated with the energy of that state. And that means our preparation for all practical purposes is just like a thermal bath, a certain temperature T1, right? We prepare the system in a Gibbs, sampling its state from a Gibbs distribution. So it's equivalent to having our system in interaction with the hot bath for some time, and then you turn off that interaction, and your system remains in that state with that probability. So now you see, actually, what we have here is a device which is in contact with two heat baths. We can choose this T1, for example, as a larger temperature than T2, and interaction also with the work source. And on top of that, we can also make measurement on the device. So basically, this is nothing but a thermal machine. And so we want to study the thermodynamics of this machine. So here is a scheme of our setup. So we prepare some state psi I, which is an eigenstate of the Hz Hamiltonian, and we prepare it with a probability which is given by Boltzmann factor at temperature T1, meaning that our initial state has some energy EI with this probability. Okay, now we start an annealing schedule. Actually, we are not doing the standard annealing schedule, but we are doing what is called reverse annealing, meaning that we start from S equal to 1 here. We go to S bar, and then we go back to 1. During this annealing schedule, you do work, and possibly your system, your chip may be dumping some energy in the cold bath, which is, so to speak, so to speak, it's the substrate on which the chip is built. No, so this bath is a phonon bath, physically speaking. And then after you're finished with the reverse annealing, you make the readout of the state again. So you're making the measurement of all the sigma z's, and you find the new final energy, and then you start over. So this difference of energy that you measure, you can also interpret it on average as the heat that your system would exchange with a real thermal bath, if there were a thermal bath. But we are just mimicking that by our preparation. So let's get now to the modeling of such system, of such situation. Basically, you can consider the chip and the substrate as a big thing that is thermally insulated, which therefore evolves unitarily. So what we have here is a cyclically driven, cyclically because our driving here is cyclical. You start from 1, you go back to 1. So it's cyclically driven. It's bipartite because it is composed of two parts, chip and, to speak, environment. And the whole thing is thermally insulated. And we are applying some time-dependent driving on the chip, but we can also see this time-dependent driving as being applied to the whole big box there. And this, on top of that, this bipartite system starts its evolution in a state which is a tensor product of two thermal states at different temperatures, and it evolves then unitarily. Here is the formula. So now the interesting thing is that in any such situation, so for any cyclically driven bipartite thermally insulated system, you have that the fluctuation relation here holds. This thing holds. In any such situation, this is the result that we have proven formally a few years ago. And as many of you probably know, consequence of that is this relation here, which you can interpret as the average. You may call this thing here sigma, the entropy production. Whatever you call it, this quantity here must not be negative, cannot be negative in any such situation. Now, let us see some consequences of this. If you combine that inequality with the fact that the change in energy in your system plus the change in energy in your reservoir is nothing but the energy that you have put in during the driving, and you combine it, you combine this uh, with this, basically you see that out of the 8 possible combination for the signs of these 3 quantities, which define the operation of your engine, only 4 survive, which are the heat engine here, as which you all are very familiar with. Refrigerator is also allowed. Another one is heater, meaning you spend energy to heat up both baths. And then there is another one which is also allowed, which is accelerator. Here heat goes from hot to cold, but you spend energy to help this natural flow occur. So what I'm saying here is, regardless of the unitary, regardless of the details, this holds for any cyclically driven bipartite system that starts in such a product state. Now, if you now make a change of variable from delta E2 to sigma, the fluctuation relation now reads in this manner. Joint probability of having entropy production sigma and energy change of your chip to be delta E1 over the probability for the same exchanges but with negative signs is as this exponential form. And for any joint probability that has this property, as has been shown by Timpanaro, Guarnieri, Gould, and Landi recently, the thermodynamic uncertainty relation holds in this form. Okay, in the paper they wrote it in a slightly different manner, but here I write it in this form. So the dissipation must be larger than some function, g, which is defined here. It's just a detail, but it's a function of what? It's a function of the average energy change in your chip and the mean square root deviation. Okay, so just like in Udo's talk, this is a universal result. It depends only on the fact that the chip plus environment evolves unitarily. So it holds always. But the interesting thing is that it gives us a way to get around a big problem that one would face when trying to study the thermodynamics of any such quantum device. Namely, all you can do typically is to measure this delta E1. You do not have access to delta E2. You do not have access to W. Only thing that you access is the chip on which you make the measurements. So how can you, for example, study the thermodynamics of this object if you only have delta E1? You want the others as well. Okay, you cannot, but at least the thermodynamic uncertainty relation here gives you some information on them. For example, here you see just by measuring delta E1 and its average value and its variance. So if I have the statistics of delta E1, I can get some information about sigma. Not only, you see, also, of course, delta E2 is also related to sigma, and also W is related to sigma in delta E2. So you have basically inequalities for both the entropy production here for delta E2 and for the work. And they are all expressed in terms of this delta E1 alone. So you make the measurements on your chip and you have information, for example, on energy, or at least a bound on the energy that has gone here, or the energy that you have spent to run this thing. I find this very fascinating. I mean, it's really beautiful. Just by looking at one part, you can get, you cannot get a quality signs, but at least you can get some bounds. And in some cases, these bounds are enough for what you are looking for. For example, in our experiment, we were able to single out which one of these 4 operations was going on. Right, so let's get to the results. First result, so in all our run, we set the temperature of the hot bath to infinity. Can you guys hear me?
Yeah, just so you know, Michele, you've now eaten into your Q&A. You've got 7 minutes left in your Q&A. In your question.
Okay, I'm out of, so I have 7 minutes plus Q&A or including?
No. You're over time. You've got 7 minutes left in just the Q&A. So you're eating into the Q&A.
Okay.
You're eating into your question.
Okay, I'll go fast now. So just the result. We set the temperature to infinity. We do no driving just to see what happens, and you see the energy goes down. So it's definitely an open system. It's not staying, it's energy, it is dumping energy in the bath. Now, this is a plot here of the average energy change of the chip as a function of a minimal value here as bar of the annealing time, annealing parameter. And you see, if you start from 1 and you go down very quickly, and if you are below S1/2, basically you reach the ground state. Same thing for the variance. The variance goes down very quickly as you pass S bar equal to 1/2. So you are going very close to the ground state if you do such an annealing with S smaller than 1/2. And at the same time, as you see here, you are dissipating a lot if you go above 1/2, which is here. This is the bound. We are plotting here this thing, which is the bound on the entropy production. So if you go below a certain value, which is 1/2, you dissipate a lot and you dump a lot of energy into the environment. So let me jump to the conclusion very quickly. If you look at the signs of energy exchanges and work, you see that this is smaller than 0 from the measurement, and this from the bounds are both larger than 0. So what is happening in our experiments is that the machine works as an accelerator. So it helps the system relaxing to the close to the ground state quickly. It's an accelerator. And we observe large dissipation as you cross the quantum critical point, which is at S1/2, where the gaps close. And that's where you dissipate a lot and you dump more energy and faster, more easily energy into the environment. So with this, thank you and sorry for being a little bit over time.
Okay.